So I want to offer to you a reinterpretation of this same equation. I do not do anything to equation, but I want to tell you another way to think about it. And I like this way better, although it's equivalent. So the way Tom introduced it was to say that this part is entropy of mixing, and this part is energy of interaction. This is how you said, right? I suggest a different interpretation of that same formula, which I call Lifshitz-like. It's like because Lifshitz himself never said so, but it's, I think, in the spirit of some of his works. So this is free energy of an ideal gas of chains. Okay, it's translational entropy of ideal gas of chains. And this is interactions. All of this is a repulsive part of interactions. This is attractive or partly repulsive, partly attractive part of interaction. This is pure repulsive. This is excluded volume interaction. So one way to think about it is to remember this picture from Michael's lecture. And remember, Michael explained that there is a sharp increase of interaction potential at short distances, which corresponds to particles excluded volume for one another. They cannot really enter into the body of one another. And there is also this possibly attraction part. So my understanding is that this part describes this part of interaction. And this part is responsible for this part. I don't understand why we should somehow say that this does not belong to interaction. Somehow it is. Sorry?
This is interaction between polymers. And the other form interaction between polymers and solvents.
Okay, you can put it this way. In any case, I insist that this is a possible interpretation, and I think it's useful in many cases. At least it is useful for you to know that such interpretation exists. Now, another thing that I want to point out and that I will need in the further discussion is that if you perform simply Taylor expansion of this in powers of small density, small phi, then yesterday we discussed the quadratic term, and Michael and Tom discussed at length what happens when chi equals 1/2, and this is the theta point when two-body term disappears. But I don't know why Tom did not write the cubic term, and there is gorgeous cubic term, which is... Yeah, okay, so the British are frequently lazy, I noticed. And this is cubic term, and notice that, not surprisingly, in this particular Flory-Huggins formula, cubic term is always positive. It's always a repulsion, and this is something Michael referred to. He said that when chain collapses into a globule, the density of the globule is stabilized by three-body interaction. This is the three-body interaction, and this is always positive because it is entirely due to this term, which is due to the repulsive part. Okay, so that I think I did not want to show, and this is a slide that is here by mistake. So coming back to our subject today, I want to talk about polymer solutions. And as a start, here is a summary of what we learned yesterday about polymer solutions in terms of single chain. So we did not study that part. That would be my third lecture next week. But we studied these three parts. saying that in different solvents, polymer chain coils up. It coils up because it likes coiling entropy. It coils up in different ways. Its size depends on the chain length in different, with different power exponents. It corresponds to different fractal dimensions. In this case, there is a challenge from Michael, and I will not provide you a hint about it, about fractality of this part. But there is this change of chain size depending on the type of solvent that you're talking about. And the summary of what Michael told you yesterday is this picture. He had similar looking picture, except I think his was black and white and mine is colorful. Was yours black and white? Okay, so in the theta solution, your chain size goes like square root of n. This is something that I called Napoleon Principle, and I do not pretend that this is particularly nice name, but I did not invent any other way to celebrate the fact that we are in Corsica, so forget it. It's unsuccessful joke. And now in good solvent, at proper place, you cross over to the power 3/5. Your chain length, chain size grows, coil size grows like n to the power 3/5. And in the poor solvent, you cross over and your chain size goes very slowly as chain length to the power 1/3. And the key here is this crossover scale. The crossover scale is something that Michael was explaining very rapidly, and so I will repeat the argument. The crossover scale is called thermal blob. Thermal blob, blob is a fancy name, but it means the scale at which there is crossover. And what type of crossover? Crossover is that at smaller length scale, at smaller lengths of polymers, or smaller distances in space, your chains do not really feel the importance of interactions is marginal. They, as Michael called it, they are transparent. They do not feel really interactions. So accordingly, you can say that up to this scale, the relation between coil size, psi, and the number of monomers, G, is this square root of length law. And also you say that interaction energy between all these chains, as Michael estimated it, it is square because you have to count all pairs of your particles. It is the number of particle squares. This absolute value of B, I will explain in a second, is characteristic of strength of interactions, and you divide this by volume of your object, and there should be KT to make it KT, but on the other side there should also be KT, so I just say it's a further one. So from these two, you find size of your thermal blob and the number of monomers in your thermal blob, and I have to explain what is this B. B, I call it second virial coefficient of interaction between monomers, and V is the second virial coefficient in very good solvent when I can actually use the fact that I do have this picture. So when this is the same picture that Michael had. We shared this slide at some point, and since then it is sitting in my computer somehow. So it's Michael's slide. I stole it.
There's no color.
Sorry?
Better colors.
Better colors, yes. My computer does it automatically. So when this repulsive part dominates, then this V is the excellent volume, and this is what is V in my notation. So V is something that happens essentially at very high temperature, when temperature is very high, and close to the theta point, this quantity, big B, virial coefficient, it goes to 0 linearly with T minus theta. You can also write it in terms of Flory-Huggins like this. Okay? And I assume for simplicity that this V and monomer size are, it is the same length scale, which is true.
This V is different from that V.
From which V?
The V in B is different from V in correlation, and same slide. This V is different from
this V is what I call big B.
right. But on the next slide,
This V is what I call big B, yes.
on the next slide, yeah, the V on correlation length should also be B.
V in correlation length, where
B in thermal blobs.
yeah, this should be big B. Yes, thank you. This thing must be big B. Yes, absolute value big B. Okay. So I was trying to explain that this is actually the property of very flexible chains. Semi-flexible chain, waterline chain like DNA, you have to work a bit harder. It's all known and written in proper places. So but I will just, for simplicity, assume that these two length scales are the same. Absolute volume and monomer size are the same length scale. Okay, so please notice this. This is very important for the rest. Okay, so in fact, when we're talking about polymer solution, this single chain story is an important introduction to polymer solution because what is single chain? Single chain is, of course, polymer solution at 0 concentration. So for the next hour or so, I will be constructing phase diagram in terms of either temperature or this quantity tau, which is deviation from theta temperature. So it is temperature and this is theta temperature. Or you can think of it in terms of Flory chi parameter that goes down and theta temperature corresponds to 1/2. I will stick to this tau. I think tau is somehow physically more appealing. I don't know, but it doesn't really matter. Also, instead of concentration, which is the number of monomers per unit volume, I will use volume fraction, the same volume fraction that Tom used in his lattice model, but I don't think in terms of lattice model, so it's just volume fraction. It's roughly speaking, the number of monomers in the volume of one monomer, so this is the volume fraction of monomer. And of course, concentration of chains is C divided by N, because for obvious reasons, I hope. So I will construct this phase diagram, and so far we know everything about what happens on the tau axis when concentration is 0. So let me go on the concentration axis. On concentration axis, there are many events happening. And first of all, I want to say that this dilute regime, when every chain lives on its own, is not at strictly 0 concentration, which never happens in real life, of course, but it is at sufficiently small concentration. And how small is small? How small is small? Every coil should sort of be far from other coils, which means concentration should be smaller than C star, so-called overlap concentration, the concentration in which different coils start to overlap to one another. And this obviously is the concentration of monomers inside one coil, right? So this C star is therefore estimated as number of monomers in one chain divided by cube of the size of one chain, and this is the answer, and in terms of volume fraction, it's nicely or simply 1 over square root of n. So as long as our concentration is below this 1 over square root of n thing, we are in dilute solution, and dilute solution, we know everything about dilute solution. Wonderful. So now, at concentration C equals C star, we have sort of overlap. These coils just touch one another. Just at higher concentration, but still concentration small compared to 1 over volume of one monomer, which means volume fraction is still small, but coils strongly overlap. This is something, dilute solutions exist in, I don't know, if you take sodium chloride and put a small amount of sodium chloride in water, that would be dilute solution of sodium chloride. Seawater is a dilute solution, relatively dilute solution of various salts in water. But this is something that is specific for polymers. Only polymers exhibit something like this because overall concentration is still very small. Volume fraction is still very small. It is almost pure solvent, but nevertheless, coils strongly strongly overlap, and this is because volume fraction inside one coil is small. Okay, and then there is, of course, concentrated solution, of which I will not speak very much. So really the most interesting novel case would be this semi-dilute situation. Okay, so now let's talk about essentially what I did is I walked you along this line, along the line of theta point. And more or less you can imagine that, it's not quite true, but more or less you can imagine that in theta point, all coils are Gaussian, whether they overlap or not. So it's more or less true. And this remains true as long as this condition that interactions are not important is valid for the whole chain. In other words, as long as the thermal blob is bigger than the whole chain. Okay, so if would-be thermal blob is bigger than the whole chain, then the whole chain is transparent and does not feel any interaction. And so you can easily analyze, when you remember what is the thermal blob size, you analyze it and you discover that this is true when absolute value tau, deviation from the theta point, is smaller than 1 over square root of n. So in this narrow strip along the concentration line, your interactions are unimportant and you are more or less in, it's a set of ideal chains, of which we understand pretty much everything. So what happens next? Next, let's go downwards in temperature, below this yellow theta region. Let's go downwards and let's see what happens. Well, in some sense, this is what Tom's lecture was all about. What happens is there is phase separation. There is phase separation, which means on the phase diagram of temperature and concentration, there is this two-phase region, which is green here. And if, for instance, you fix your tau to be negative below theta point at this level, and your overall concentration is somewhere here, where Tom was showing his common tangent construction, you will see that your solution separates into this and this, and part of solution goes into one phase, part goes to the other phase, and how much goes into the one phase or the other depends on where in this segment where you are. there is proportionality relation, which is beautifully called Maxwell-Lever principle, I think, but it's, I think Maxwell invented more interesting things. So how do we find these two coexisting concentrations? Well, two coexisting concentrations because chains can go from one phase to the other. There is a condition that chemical potential on both sides, or in both phases, chemical potential of chains should be the same in both sides. And chemical potential consists, of course, of the part that is ideal gas of chains and some contribution due to interaction between particles. Same thing on concentrated size. Ideal gas of chains, so this is chemical potential of ideal gas of chains, concentration of chains, and there is interaction part, some interactions. The difference is that on the dilute part in poor solvent, as Michael told you, consists of these globules, separate globules. And therefore, you have to worry about surface energy of every globule. Okay, so there is surface energy of this globule, and you solve this, and you discover this simple formula. Because otherwise, interactions inside this macroscopic concentrated solution and inside the globule are the same. It's densely packed system of thermal blobs. Same thing, no difference. If you live somewhere inside here or somewhere inside here, you cannot tell the difference. It's the same thing, the same material, same density, same everything. So there is no reason why it should be different. So this contribution of interactions is identical on this side and on this side, and the only difference is this surface energy. So if you consider, you discover that there is this relation, and if you more specifically realize that the surface energy of the globule should be just kT per one thermal blob, and you go and count how many thermal, you know the size of thermal blob, you count how many thermal blobs on the surface, you discover this formula. I forgot to write it on the slide because I thought that Michael would derive it, but he didn't, so that's okay. It is just simple algebra. As I said, you just count how many thermal blobs on the surface, you find. But what I want to emphasize is that this relation is entirely different, in violation of Flory-Huggins prediction. This is where Flory-Huggins theory badly fails. This is something that Flory-Huggins theory does not capture. Why it does not capture it? Because how do you imagine what happens in this phase according to Flory-Huggins theory? Flory-Huggins theory imagines that there is very small, but uniform density or uniform concentration. Super small, very small concentration, but it's uniformly smeared. Well, in fact, if you have chains, monomers are connected by chains, they cannot smear at very low concentration. They cannot go to concentration smaller than concentration of monomers in one chain. So what happens is this very low concentration gets clumped or grouped into these pieces, globules. You have indeed very low concentration. In reality, it is so low, the concentration, you see concentration dilute phase is so low that in a real experiment it's super difficult to see anything there. It's for many years was controversial if any experimentalist was ever able to see any polymer chains in this dilute phase. They said it would be elimination, blah, blah, blah. It's very difficult to measure. So it's really, really, really very dilute. And so I would say this question of deviation of this result from Flory-Huggins theory is, to me, mostly of academic interest, but I think it is still interesting. Okay, so this is poor solvent. By the way, you guys are abnormally quiet. I know you got tired of yesterday, but you have many days in front of you, so you should energize yourself, please. Michael always wants to ask questions. Yes, Michael.
You need to balance osmotic pressure to phase?
Of course, yes. I need to.
Should we give you something else, something different if you do that? Because you're using only one equation.
Yes, of course, yes, yes. I surely have to balance osmotic pressures. It is.
Changes the equation.
We can indeed. I can come back to it. I will come back to it. I have a slide about it. But let's, well, since the question is asked, let's answer. To the first approximation, osmotic pressure of this and osmotic pressure of this is 0 to the first approximation, because density of this concentrated phase as well as density of the globule corresponds to the balance between attraction, two-body attractive interaction forces and three-body repulsive interaction forces. And so these two factors compensate each other and lead to 0 osmotic pressure. On this side, osmotic pressure, you can say osmotic pressure inside one globule is 0. It is first approximation. In the more careful approximation, on this side, you have to take into account osmotic pressure, which is the ideal gas of these separately moving globules. It's very small because concentration of globules is C dilute divided by N, because it's the concentration of chains, not concentration of particles. So it is very small, and this is a very small correction which have to be taken into account, and this is important correction, so I have a slide there. But the first approximation is 0 on both sides. Okay? Oh, wonderful. Thank you. Yes.
What is the order of magnitude that dilute phases have?
What is what?
What is the order of magnitude for the concentration in dilute and concentrated phase?
Okay. In concentrated case, if you are not particularly close to the critical point, concentrated, it goes linearly, so it's significant concentration. In dilute phase, I have an answer to you, because this is numerically computed by nodal and spinodal lines in this situation, not according to Flory-Huggins equation, but according to essentially this. And for instance, yeah, so it contains a little more information that you need, but you see that these concentrations are exceedingly small. This is logarithmic scale, and this concentration here are very, very small. Just read the line here. Any other question? Let me look at my watch. Okay, we are doing well. Okay, so back to the good solvent situation, let's check. So far, we know that there is overlap concentration in the theta region. Here, coils do not overlap. Here, coils do overlap. Let's see what overlap concentration is doing in the good solvent regime. So this is pretty easy to do because dilute solution consists of swirling coils. Each has this size. So how do I know this size? And by the way, this is something useful for you to know. Whenever you have a situation like this, you just write what you know. You know that swollen coil has the size of monomer size times the number of monomers to the power 3/5. This is how you write it. Monomer size is now thermal blob. Number of quote-unquote monomers is now number of thermal blobs. And the rest is algebra. Oops, sorry. Okay. So if you remember what is thermal blob and what is the number of monomers in thermal blob, you just go through the algebra and you obtain this tau to the power 1/5. And Michael, in some form, referred to this 1/5 power in his lecture yesterday. Okay, so then overlap concentration is the concentration of inside monomers inside one coil. And this is what you have. It is like this. Okay, so it's a line like this. So really dilute solution exists now in this sliver of phase diagram. Okay, so notice that important point when you deal with such scaling relations, important point, every time, on every step, you have to check that different parts smoothly connect to one another. And in this case, at the critical value of tau, where chain starts filling its interactions, when chain stops being transparent, at this tau, these two it basically should be the same. Because remember, this is nothing. This line is not phase transition, it's not lack of analyticity. This is just a crossover. This is a smooth line, which we draw as a line because we are used to make log-log plots. In log-log, it's almost invisible, the width of it. But in reality, of course, there is significant range of temperature where it's neither one nor the other. So therefore, this and our regular 1 over square root of n should be the same when tau is 1 over square root of n. Indeed, if you go there and put tau equal 1 over square root of n, you come back to what you need. Okay? So just if in one of the next slides I forget to do this, remind me. Any questions? Yes?
Could you maybe go over again exactly what tau is?
Exactly what tau is. Tau is the most important player of this story, and therefore I am glad to repeat it. Here is your tau. This t minus theta divided by, it should be written somewhere. I forgot where. I'm sure in some place in one of the slides it will be. Here.
And how physically should we think about tau?
How physically we should think about tau? You should think about tau as deviation from the theta point. So when you go to a doctor with some, God forbid, some illness, and doctor asks, what is your temperature? And you say, oh, it is 39 degrees centigrade. In the future time of reason, instead of telling 39 degrees or proper number of degrees Fahrenheit, you would say tau. My tau is 2 degrees. So this is how we should think. Sorry? Oh, okay. It's 200. It's 2 degrees divided by 300 degrees. It's 1/150. Yes. Okay. This is how you should think about tau. Tau is a I will probably refer to it as a temperature, but really it is dimensionless deviation from theta point. Any other question? No other question? Let's go further. So now we step over this crossover line into the famous semi-dilute regime, in which I told you concentration is still small in the sense that it's mostly pure solvent. Very small percentage of volume is occupied by polymer chains, but the picture is pretty much like this. So it is a reminder of our friends thermal blobs, and our chains consist of thermal blobs, but there are many thermal blobs in each chain. And now I want to address, yes, please.
Sorry, we've been talking a lot about thermal blobs, and we went over it very quickly yesterday. Can we just have a quick recap of that? I feel like I don't fully understand what the thermal blobs are.
Okay, I attempted to do that. Let me go back. And okay, so here is my reminder about thermal blobs. So thermal blob is the length scale and number of monomer scale, which is a crossover between short chains, short pieces of the chain that do not feel interactions. They are ideal chains, short pieces that are ideal. Their size goes like square root of their number of monomers. They are ideal, but they are on the verge of becoming non-ideal, of becoming exciting rather. They are to cross over to the regime of significant interactions. So in order to find this size, you say that up to the scale of thermal blobs, you still have this square root of n law, right? And the amount of interactions is right here. Amount of interactions is the strength of interactions times the square of the number of monomers in one blob and divided by the volume of the blob. You go through the algebra, you discover this. Modulo the fact that I assume that V is BQ. You comfortable? Anybody else?
Can I maybe ask a silly question? Why is it useful to use thermal blobs? Why are we talking about thermal blobs? What's the advantage?
This is a difficult question to answer. Why do we do anything? Okay, but I am prepared to answer it. In fact, I have a good answer to this. Why do we use thermal blobs? Because it would be difficult for you to memorize this formula or any analog, while to memorize this formula is easy and convenient, because when you think about your chain as consisting of thermal blobs, that means you don't have to worry every time, oh, there is crossover at small length scale, there is Gaussian at large length scales, it's something else, difficult. As a short step, you say, oh, if I think about my chain in terms of thermal blobs, then this chain is either a globule, which means dense like this, or it is swollen coil with this power 3/5, Flory coil, or it's Gaussian coil. But you have to only remember three things: globule, swollen coil, Gaussian coil, that's it. Everything else is hidden in this. You say that now your effective monomer is thermal blob size. Your effective number of monomers is the number of thermal blobs. And then you're done. And I will do it all the time. Okay? This is why we think in terms of thermal blobs. Is it clear? It's convincing? Okay. All right. Okay. So now I want to know something about this semi-dilute solution, and a good way to start is to find the quantity which is called correlation length, and which is the following. Suppose I am this particular monomer. Okay, so now we live on this planet, Earth, and we look for aliens. Hey, are there aliens somewhere? And so far it seems that we are alone in this universe. We didn't find anybody on Mars, on Jupiter, on maybe on other planets with other stars, and so on and so forth. Imagine that at some point we find some other civilization, and there is summer school over there. They teach polymer physics, and we start talking to them. They look just like us, very good. And the question is, what is the distance to that place? So very similarly, the idea is that this monomer looks around and where are other chains? So this psi is the average distance from given monomer to monomers of other chains. Okay, so in order to find this psi, I will think about it in the following way. Let's take one particular monomer here on the red chain, and let us think about a piece of this chain which is S monomers long. S monomers long. So I would call, similarly to the word classmate or roommate, classmate is the member of the same class, roommate is the member of the same, inhabitant of the same room. So chain mate, I would call it. So monomer of the same chain. So how many monomers of this? I consider a piece of the chain of S chain mates of a given monomer. So how big is this piece of S chain mates? Well, here is the answer again about why we use thermal blobs. Here is thermal blobs, the size of thermal blob, the number of thermal blobs in this thing. So this piece of the chain, this group of chain mates, is set of thermal blobs. So this is the size, same story. And then I would say that concentration of these chain mates is just S divided by a cube of the size. Michael was talking all of this, doing all of this in space of dimension D. Since he didn't find experimentalists to work in 4D, so let's do D equals 3 for now. So concentration of monomers inside this is this. And so you find this concentration, right? And now I claim the following. You see this concentration drops as S increases. As you take bigger and bigger piece of the chain, the concentration drops. So close to you, there are many of your chain mates. But the further a step, more and more dilute is your coil. More and more dilute is your coil, but when the concentration of your chain mates drops below average concentration of the solution, then your relation to these chain mates is somehow diluted, and at larger distances, most of your neighbors are not your chain mates, but just members of other chains. So therefore, I would say that this is the scale at which something happens, and specifically, this is the scale at which our chain reaches correlation distance. So there are two quantities, G, the number of monomers inside this distance, and psi, the distance itself. And if you go through algebra saying that this is equals C, average concentration, so you go through the algebra, you discover this result. Okay, so this correlation length psi is, of course, monomer. It's controlled by the monomer length scale, and it drops with increasing concentration. The bigger is concentration, the closer is your distance to the alien monomers. This is natural, but of course, you have to work harder to discover that this law is the 3/4 power. Okay, so you can say that this number of monomers and this correlation length are number of monomers and length and size of new blobs called concentration blobs. Yeah, there are many blobs. There are many, many, many blobs in life. Life is blobby, I would say. And this is concentration blobs. All blobs are basically crossover length scales. So once again, thermal blob is a crossover from Gaussian behavior to maybe non-Gaussian behavior, from Gaussian ideal coil behavior to behavior in which in which interactions are important. And concentration blobs is a crossover from the situation when your chain, your piece of the chain is almost like it is in dilute solution. This piece does not feel other chains. And on larger length scales, these blobs are at overlap. So on larger length scales, indeed chains overlap and strongly entangle. Yes?
So this side is the radius of this blob, and the R, I don't understand what is the R.
This R? This R is the size of a piece. If I take a little piece of length S monomers, and I want to know the size of this piece. When R reaches this, when S, the number of monomers, reaches one blob size, reaches G, then concentration inside this radius becomes equal concentration overall. Concentration, local concentration here.
So is the radius of the small,
the radius of this small blob is this psi t. It is thermal blob. The radius of this small thing is the thermal blob. This is the size of thermal blob. And you see, these thermal blobs are not at all densely packed because there are lots of free volume here, Lots of free volume everywhere. While these blobs are densely packed, roughly densely packed. So this R is the sort of construction. It is moving. I will not later use this particular R. This R is the size of little piece here. And then I consider that this gets bigger, 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 bigger. Its concentration, its internal concentration gets smaller, 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 and dives below the concentration outside. Okay? Is it better? Feel more comfortable? Good. Okay. Any other questions?
I'm struggling to understand why it dives below the concentration, like the average concentration.
Well,
I guess maybe I don't fully appreciate what that graph is showing.
sorry?
I guess I don't fully appreciate what CS with S is showing.
Okay, so S, I start from one particular monomer and consider its neighborhood of S monomers. And I consider concentration of this piece, concentration created by this piece, only this piece.
The piece being a thermal blob or the whole monomer?
The piece is piece, that S monomers, several thermal blobs, So this is the number of thermal blobs in the piece. And this is the size of thermal blob, so this is the size of this piece of S monomers. So the concentration inside the size, inside this piece of S monomers is just like this.
Only monomers from the red chain. Right?
Self-concentration, not only red chain, but self-concentration of this little piece of S monomers of red chain.
And that keeps going down because the volume of a single chain polymer grows faster than the number of monomers in it. It is a fractal.
Because
The volume goes into the half, so the volume goes into the free of the two. So the number of monomers only goes down.
Okay? Very good. Thank you, Tom. Thank you, Michael.
The point is, this is very subtle. It's very subtle, and people have been thinking about this for 50 million years, like you and me, Mark. It's kind of obvious, but it's very, very subtle that when the self-concentration, as it goes down and down and down and down and down, just the self-chain in its whole volume hits the bulk concentration. That's what the picture looks like. I think it's a very hard thing. I think it's very subtle. If you really study
I agree. I agree.
That's what it must look like.
I agree, which is why there is a whole slide about it. It's a subtle point.
And we are slashing it.
Well, look.
It's a lovely slide, but it's a subtle thing.
All right? Okay? Yes?
When the blob size is changing, is the correlation length changing also?
What do you mean blob size is changing?
In different solvents, when you
Yes, correlation length, of course, changes because correlation length and size of the concentration blob is the same thing. It's by definition the same thing. Correlation length changes if tau changes, then correlation length changes. If concentration changes, correlation length changes, yes.
But when you change the concentration of the graph here,
Ye-
there's the thermal blob doesn't change.
Thermal blob doesn't change. Yes, because in this picture, I assume that temperature is fixed. But if you want me to construct the picture in which temperature also changes, always three-dimensional picture will be difficult to understand.
We just thought of another helpful way of saying it here.
Okay, please.
That's why we're whispering, but it's to a purpose. That you can think of the semi-dilute solution as a concentrated solution of correlation blobs. As a melt even. As a melt even of correlation blobs.
Absolutely.
So they're just close by tightly. The correlation blobs are packed together and fill space.
Which is written right here.
There you go.
You can think, I repeat, you can think of semi-dilute solution as concentrated solution of concentration blobs, or melt of concentration blobs. Because concentration blobs are constructed such that they occupy all space.
In fact, RDS and CDS is a way to know where is the correlation length.
Yes?
It's a method to reach what is the correlation length. RDS and CDS.
Yes?
Could we,
Yes?
what can be measured?
What can be measured?
Yeah, directly. But what is the quantity you can measure on the solution?
Well, you can measure different things. You can measure, we will go there. You can measure, for instance, you can measure osmotic pressure.
Can we measure the correlation length?
Yes, you can measure correlation length, but I will be mostly speaking about osmotic pressure. And osmotic pressure we will discuss. Osmotic pressure is directly related to this. So
Scattering.
yes, of course. Yes, of course. By scattering, you can measure correlation length directly. Yes, of course.
Just draw the S of Q. Sure.
Well, I don't want to go too much there, so. Okay, so good solvent. How do we use correlation blobs? This is to answer further your question about thermal blobs. Why do we speak about concentration blobs? Because we can use concentration blobs in very much the same way. We will say that on larger length scales, concentration blobs, these chains of concentration blobs are ideal chains. And Tom explained this yesterday. He was telling you that if he is in some densely packed New York subway where he touches somebody's leg and he doesn't know whether it's his leg or somebody else's leg. So the same story here. This blob doesn't have any way to know whether it belongs to the same chain as this blob or the same chain of that blob. The blobs are the same. So therefore, this chain of correlation blobs, chain of concentration blobs is now ideal chain. It's a Gaussian chain. And I told you yesterday morning that in concentration system, for some wonderful reason, deep reason, chains are ideal. And so this is ideal chain of concentration blobs. How do I deal with ideal chain? The word ideal means power 1/2. Everything else, I do the same trick. The size now of a monomer, quote-unquote monomer, is a concentration blob size. The number is the number of concentration blobs And then you go through the algebra. Here is a reminder about the concentration blob. You go through the algebra. You discover that, of course, R, as its Gaussian chain, there is n to the 1/2 dependence, but depending on the concentration of solution, the size of your chain changes with very small power, but does change and become smaller as your chain becomes, as your other chains become more concentrated. So the rule, again, we have some complicated formula. So let's check what happens in a reasonable limit when we know what should happen. For instance, what happens if phi goes to 1 and tau goes to 1, which means athermal solvent, very good solvent. Okay, so it is essentially melt of chains, and you are back to your Gaussian size, b n to the 1/2. Smoothly, nicely, and so on. Any other questions about concentration blobs?
Could you remind me why there's a power of 1/2 and
This is because the chain of blobs is an ideal chain. It's an ideal chain. It's Gaussian chain. It's Gaussian because these blobs, they, scientifically speaking, they screen each other, and this blob does not distinguish between other members of the same chain, other blobs belonging to the same chain, or blobs, similar blobs belonging to other chains. The same thing. You see, the real chain in good solvent swells because every monomer repels from every other monomer. And so in order to gain energy, they sacrifice some entropy. They swell, they do something that they don't like in order to avoid company of each other. In this case, there is no chance to avoid the company because your company is everywhere. You cannot possibly reduce your chances to meet other monomers if your coil swells, because if it swells, it meets other coils instead of just going to empty space.
But it's only half above the concentration blob size.
It is only true above the concentration blob size. As well as inside the thermal blob. Inside the thermal blob, remember, there was the same story. Inside, it was Gaussian. Then it became, let's say, 3/5, exclude volume thing. And then up to the correlation concentration blob, it is real chain with 3/5 and so on. And above concentration blob, it is again Gaussian. Here are many crossovers. So if you take chain section of S monomers, S goes from 1 to the full chain size N. If you go through these, there are two crossovers, the thermal blob and concentration blob. Up to the inside the thermal blob, it's a Gaussian chain. Outside of concentration blobs, the chain of concentration blobs is Gaussian again. And here in between, inside one concentration blob, there is this Flory 3/5 power of chain in a good solvent. they scale the same way. It can be radius of gyration of the section of size S, or end-to-end distance of the subchain of the size S. They scale the same way, so I refer to them as size. Okay, so here is another way to derive these results, which is a beautiful argument, which is called scaling. And the argument goes like this. I illustrate it here for chain size or for correlation length. You can use it for anything. So let's, for instance, talk about chain size, this line. So I will walk you through it, and this is really simple. When you master it, it's really simple. So first of all, you say chain size should be Flory chain size, which is characteristic of the dilute solution. And there should be some function of concentration divided by overlap concentration. And this is because there is only one length scale of the coil, which is the coil size, and therefore there is only one characteristic concentration, which is overlap concentration. There are no other scales of concentration. So therefore, there must be a function of this ratio of concentrations. Furthermore, you can guess that this function should be a power law function. What else can it be? In the fractal, where everything is power law, so it should be a power law function with some unknown power y. You see, for correlation length, same argument, except power is called x. And now you go through algebra, you remember what is your Flory radius, you remember what is concentration, and they are written here as a reminder, and you go through the algebra, you discover that there is y everywhere, it's a very easy algebra, and now you know that this chain size, eventually at sufficiently large chains should become again ideal Gaussian, because of the argument that at high concentration you don't know who is your neighbor, whether it's you or somebody else. So it should be n to the 1/2. So you say that this power should be 1/2. You discovered that this y is -1/8, and you rediscovered the same answer as before. Easy. Very, very easy. So what are the steps, automatic steps? Power law, algebra, and then physical argument. Your physical argument in this case that this guy should go like n to the 1/2 for correlation length. This correlation length should eventually become independent of the chain length, because the distance to the nearest monomer is, of course, independent of where are the ends of your chains. So similar argument here is for osmotic pressure. Osmotic pressure, for ideal gas, I derived it for you yesterday. This is called Van Gogh's law, and it is ideal gas of chains, concentration C divided by N, and ideal gas in this case would be, osmotic pressure in general, in semi-dilute regime. You go through scaling argument. You say that this is ideal gas pressure times some function, actually power law function, of concentration divided by your only concentration scale. This is a subtle argument. Yes, Tom said the previous slide was subtle argument. This is also subtle argument. There are many subtle arguments, which is why there is summer school. And you ask questions and you get your subtle arguments. They become less subtle for you. This is the purpose of it. Okay, so in this case, you go through algebra. And what is the physical argument? The physical argument is that this osmotic pressure should not depend on N. Because of the picture, remember this picture? Densely packed system of blobs. So where the ends of these chains, by the way, these ends are not even featured in this picture. The ends are somewhere. You can insert some semi-permeable membrane. Remember how you measure osmotic pressure? You have semi-permeable membrane. You have to introduce a bubble of semi-permeable membrane here, and this bubble will swell or collapse depending on osmotic pressure. So it should be dependent of N. Independent of N, you discover what is your power Z, and here is your answer. Now I want to emphasize that Tom McLeish yesterday was telling you about Flory-Huggins equation that predicts osmotic pressure to be proportional to phi squared. Remember, there is phi squared, 1/2 minus chi, and all of this, and this is not square. 8/4 would be square, but 9/4 is not square. Some people call it Degen's law, but in any case, it is not square, and this is not square because of correlations. These monomers are correlated to one another. They are connected by the chain. There are strong correlations, and these correlations lead to, again, to deviations from the predictions of the very simple virial expansion prediction of pressure being proportional to square of concentration. So I have about 10 minutes, I think, or so.
I think not that many.
Not even that many.
We should have the break normally in 3 minutes. So.
I thought it's until 10:30.
Well, if we want to have coffee, 10:20 to 10:40.
I see, okay, all right, okay. So here is the picture that I took from the paper, which of course, the picture I took from the paper, but this reference to the paper I took from the book by Michael Rubinstein and Ralph Colby, and this basically confirms the story about this. Okay, so I told you everything about this semi-dilute solution. Now I have to tell you a little bit about concentrated solution. Not much time for it, but the only thing that I will tell you is that you can go through the same type of scaling argument again, and you discover all of these quantities: correlation length, chain size, osmotic pressure, and osmotic pressure proportional to phi cubed, because second virial term is very small. You are very close to theta point, and your third virial term, which Tom did not write, is what happens here. So there is, this is what I explained here. So the quadratic term disappears, and on the third term exists, and so on. You can actually derive these scaling relations in this region by applying scaling arguments, crossing this overlap line, crossing this crossover line this way by changing tau, or this way by changing concentration. All of this reproduces the same results. Concentration dependence of chain size. Chain becomes, it's very swollen, becomes smaller. Sorry, this is green line is chain size, and purple line is correlation length. And so in semi-dilute regime, both of them drop. Okay, and here is a summary of this whole story. This is phase diagram in full glory, in which in every region you have these results for correlation length, for chain size, and for osmotic pressure, all of which can be measured experimentally. and there is two-phase region and everything else. So this is the whole summary of this story. So now there are open issues, and this will be my last slide, promise. Open issues. So one open issue is, of course, what happens inside, around this critical point. Those of you who have physics education remember that around critical point there are various fluctuations and so on, and this is not an exclusion. There are some issues about critical point. Now the question in the region 2, I would say the question is the following. Polymer chains are Gaussian in the bulk, but how do they behave at the interface? Since this is the boundary between, okay, so since this is on the phase boundary, concentrated solution is in coexistence with dilute solution. So concentration in the system should behave more or less like this as a function of coordinate. So in bulk, dilute phase concentration is very small. In bulk concentrated phase, there is some concentration, and there is some interface. Okay, so the interface, of course, becomes wider as you approach critical point 1. But in general, one question is how the size of this interface is related to the size of one chain. Because we are talking about macroscopic phase segregated solutions, so chains, there are many chains. And if you are not very far from this critical point, this size must be large compared to one single chain. Now, if you think about chemical potential of a monomer inside this region, as I told you, concentration of concentrated phase is basically, to the first approximation, is the balance between repulsion in second in pair interaction and, attraction in pair interaction and repulsion in three-body interaction. It's a balance. So when concentration becomes smaller, then three-body interactions, which go proportionally to cube of power, they die faster than two-body interactions. And therefore, in this surface region, inevitably, you have a potential dip, a gutter of some sort. There is a gutter, and therefore, for chains that live inside there, and you remember they are Gaussian chains to the first approximation. So for them, this surface plays the role of a potential well. And chains from inside, in some way, they are like Michael mentioned yesterday, absorption of chains on the surface. So chains from inside somewhat absorb on this surface. This has to do with the question that Michael asked me about balance of osmotic pressures, and this has to do with the balance of osmotic pressure. I can tell you that Michael and I and Ralph were discussing this question about, what, a month or 2 months ago. This is not completely understood. We did not return to this. I suspect that Michael and Ralph and I came to somewhat different conclusions. So what I am doing in this slide is I am bringing you to really forefront of what we are thinking about. So this is my last slide.
Thank you.
I wanted